Hey, good evening, everybody. Let's get started. 6 o'clock. Tonight, we were supposed to discuss about this very interesting concept of procedure writing or function writing. Uh, who like hopefully you have reviewed that already, and you know probably come to know that like programming style wise, like paradigm wise, assembly language is more like this functional paradigm. It's not a object oriented paradigm at all that possibly you are more used to think of a solution for a given software problem or stuff like that. It is functional paradigm, so we need to get used to that paradigm as well, like functional programming. Uh, the base and fundamental of the functional programming is the ability to write function and use it from other functions or the main program. That is the point for any functional programming language. Assembly language is not different from that one. We have seen that how we can define a function in the assembly program and how we can call them, how we can return back to the caller, all this mechanism we have learned. So any question on those topics? In the meantime, let me see if we have anything on the discussion. I believe I have one. Okay, it's from the Brian Blue, saying that for RT storage, why it is required that we have some extra 4 byte between SP and the sub register. Why does SP need to be a capable of double word push? This is Brian. That's just a convention that you we make a space reservation for like double word push capability, and we keep it like this. Okay. Now, can we optimize on that? Yeah, definitely. We can, like, let's say if we are creating the next frame, if we means as a, like, you need to think of from compiler perspective. Like, no one program in assembly language, right? It's a compiler that translate your high level program or program written in the high level language into the assembly level program, right? So from that perspective, uh, compiler could have taken extra steps to optimize it, and there are many optimization mode in the compiler that can be invoked. Uh, and then it can actually compact that space as well. Let's say if it is if it is the part of the memory that extra uh, space we reserved for the double byte storage after the frame, if it is not used, then we can actually, like, means again the compiler could have compacted that and start the next frame right after that one, but that needs some processing and bookkeeping to make sure, hey, this memory space is not utilized, stuff like that. So little bit complicated process, and then it will degrade your compiler runtime performance, compilation performance, the time it needs, and it need to keep track of all this extra information for that. That's why in general, like less optimization mode, compiler keep it aside. Like, okay, you use it, no use, okay, fine. 4 more bytes is lost, that's fine. But if you want to really compact your memory footprint for your application for big programming, you probably need to look at like more advanced optimization option in the compiler. Okay, but when you are writing the program yourself in the assembly program, you could have choose that. Like, it's no one is basically preventing you not to do that. But we will be following that same convention as compiler normal mode does, is that okay? Is reserve the space and keep it like that. Okay. Brand makes sense on that.
Yeah, that makes sense. Thank you.
Okay. Any other question from anyone?
Professor,
Yes.
rather than a question, I just wanted to make sure that I understood the concept. In the lecture videos, you mentioned when we're saving the stack pointers and the variables or
Mhm.
registers that we needed,
Mhm.
like S0, RA, and FP. So
Right.
you start off by using save word. Well, you start off by moving the stack pointer down
Mhm.
20 bytes, and
Mhm.
then you save
For that
frame.
example, by the way, right? It is not that 20 byte always. It depends
Yeah,
on.
yeah, just for that example.
Yes. Mhm.
So and then you save the content of frame pointer in uh, 20 bytes above stack pointer
Right. Mhm.
that's in the memory.
Mhm.
Okay, and then you proceed to save all the other um, contents of the register like RA, A0, and S0.
Right. Mhm.
And then you, at the end, you do add I. Um, so essentially what you do is you set the address of frame pointer to um, 20 bytes above stack pointer. Is that what that was?
Uh, yes. So it is not address the value. You should use the word value.
Value. Okay.
Right. And after that, whether that value will be used at the as an address or not, that's a different story. But
Oh,
here,
okay.
in this context, in this process, what we're doing, we are moving down the stack pointer from its beginning to towards the end. Like it grows down, right, from higher
Mm-hmm.
lower address. So we are moving the stack pointer from upward to lower, and then we are storing with respect to that stack pointer, that position. With respect to that, we are storing the frame pointer, RA, all the register that we need to save in the frame. And then after that, our intention is to keep the frame pointer value to the start of the frame. So stack pointer was moved from here to there. We want to make sure the frame pointer is pointing towards the old value, towards the uh, that old value of the stack pointer. Basically, frame pointer is having an old value of the stack pointer. That's what we want to make sure there.
Okay.
Right?
All right.
So yeah, so those kind of those part call this stack pointer, frame pointer moves almost in pair. First stack pointer goes down, and frame pointer then keep pointing to the older location of the stack pointer, which essentially means it is holding the older value of the stack pointer. Okay.
I had just a quick like confirmation question.
Yes. Fine.
I know this doesn't probably doesn't apply, but like I just wanted to like really make sure. But for
Mhm.
the program assignment 5, we don't need to worry about like restoring the RTE or anything, right? The runtime environment.
For assignment 5, okay, what is that? Let me review that assignment. What it says? Assignment 5. Oh, iterative factorial. Iterative factorial, what is this? No, it is this piece of code you need to write within the main, what we call it a main
Yeah, yeah,
function body. So there is nothing called a
yeah.
procedural call or anything like that. So
Okay, yeah. I thought it was like that, but on the assignment it said like I needed to look at lecture 12, so I was afraid that those two things like applied with each other.
oh, no, no, no. Well, I think I don't know what I mentioned there. My intention is that this there is a factorial example in that lecture 12, which is does a factorial, but that's in a recursive functional way.
Yeah,
We
I
are
remember that.
not looking forward for that one.
Okay.
I have seen in past student actually basically copy pasted that function and as a like put that assignment. That's
Ah,
not the target of that assignment. It is we want to make sure we understand differentiation between a recursive procedure and iterative implementation.
Yeah. Okay.
So
Oh,
that,
actually, also while we're on that topic, for factorial, is there like a zero case where it's like equal to one
yeah.
or something?
Mhm.
Zero is one, right?
Yeah.
And then we okay, that's it. Thank you.
Okay. So while we are on this topic, let me clarify one thing. So I think in the discussion, Kevin did mention this some pointer error that I made mistake on the previous lecture. Let me see who did that. Kevin, right? Oh, no, Ricky said that. Okay. So let me share that. What I made mistake there. Okay. So basically, if you look at this calculation, yeah, this is wrong. This is 2 to the power 5 is 32 actually. Okay, it's 32K. So essentially from a point like test and jump instruction point, you can access like 32K above that many instruction and 32K below that many instruction. Like you can jump back 32K as max as possible, and you can jump forward 32 key instruction. That is the max limit on that. So essentially you can access total 64 key instruction around. Okay, so make sure, please note, this was like 2 to the power 5 is basically 32, it's not 16. Okay, all right. Let's do just let's make sure you got couple of point correct in this from this discussion. One is the stop sharing. One is this the general structure of the procedure, how it looks like, right? So this general structure has it starts with a label. Okay, it starts with a label, and usually I would suggest to give a label as a function name, whatever you name you may want to put on your high level program, similar to that. For example, factorial will, let's say, give a name of factorial colon, that becomes a label. You could have used any other thing like L1. No one is preventing you to do that, but it's a good practice. If you are writing a function, just give the function name as a label. So let's say it's a factorial function, as an example we did in the class, in the lecture video, not in the class, in the lecture video. Factorial is a label. Then it follows with a, store, frame store, right? Frame, we call it a runtime environment storing, is a frame creation code. And usually you can spot that out as an, like, it's first is basically it's moving the stack pointer, then it bunch of store word, and then it's manipulating the frame pointer register. So this is that telltale sign of this first part of the program. And then first part of the function, you can spot it out from any code. And then it is the body of the function, right? Is the body or implementation of the function. And then it is the restoring code. So RT storing, then it becomes like RT restoring code. And you'll see, you can see that like that part of code usually is a bunch of load word followed by manipulation of the stack pointer. Okay. So it is the RT restore code, or this part is basically frame deletion. And then it followed by jump register $RA. So essentially, this is your beginning of the function, and this is marker of the end of that function. So essentially, this is the general structure of a function. And if it is a recursive function, then a telltale sign would be something like your body implementation part has a jump and link JL to the same label as this function has, function's name, factorial. So if that is the case, like if you spot out there is a JL in this code, which is calling the same function itself, that's a telltale sign of it's a recursive function itself. Okay. Now the question becomes, how do we use that? We define it. How do we use it? So inside your program, like let's say inside your program, you have like some statement, I don't know, some random statement. So ultimately it follows with jump and link. And let's say it's a part of the main program. So I used to call that level as main level. And then it basically rest of the program. So this is how we use it. This is how we use this function. So at that point, what happens, your control jumps to here, but it also has a side effect. Your RA register has the next instruction address. Now, what is that next instruction address? This is basically the next instruction address of this JL, like the very next one. Let's say this one is the very next one. So it has the address of that instruction it stores. And that's why at the end of the function, when it do a $RA, where RA is basically storing your next instruction address, your code jumps back to the next instruction from the calling point, from the caller, like of the caller. So main is calling here your factorial function, and once it is done processing, it gets back to the next instruction of that calling of factorial. So that's the main concept here. So I hope you guys all are clear about these conceptual things. One more suggestion I would make here. You basically do follow one convention, right? For example, I follow this convention. I always start with my main program at the beginning, like after the text is the main program. Okay, and send back. Okay, so first with the text, I do the main program, and then I usually have a call to exit. Like you remember this macro you use a lot. And after that, I have this thing, or all the functions. That's the function 1, function 2, function 3. You basically start your function body here, right? Function 1, implementation, and then you have next function. So this is more like an like methodical way to put that, write your program. If you have multiple function in your code, you have it, then it's more like a systematic way to place things up in the code. If you do follow the other way, means like you place it on top of this, nothing wrong, like this one, and then you go this one, like nothing wrong there, like main comes at the down. That's also okay. Like if you follow that, okay, after text, you have all the function body, and then you have the main. That's also okay. Um, but don't mix up like some function up, some function below. It's not, first of all, doesn't look nice, and it is not much systematic way. Okay. This is suggestion only. Question. Okay, then we can do one thing. You remember that factorial program that we wrote down? Let's say, let us try to analyze the size of the stack that would be used in that code. Um, oh, let me share first. Share my screen. Okay, this is the program, right? And let's say I call this function with this setup, uh, like this one, right? Analyze this function to tell what is the peak stack memory usage if A0 is passed with value 10. Okay, so basically, okay, this is not for you, guys. This doesn't make sense. So this is more like an like I'm setting the A0 register, let's say, with a 10, and just call JL fact. Then once it returns back to this caller, by the time how much total memory was used in the stack. So that's the problem we want to solve at this point. So for this, let's do our breakout room with groups. Let me see. Okay. Brian, I will move you to other group. You are the only one on your group.
Yeah. I don't think many of my study group members are really here anymore. I'm not sure. Doesn't happen
I
really.
have noticed that you, like, for last couple of days, you are the only one from your study group attending this.
Yeah.
I'll see. I'll check what's going on. Okay.
Thank you.
Let me open the study room, and let's take maybe 15 minutes to do this problem, and then we'll be back with the solution. Okay. All right. Open. Let me open it. Okay, I think all have came back from the breakout room. Let's see. Study group 8, let me turn back to them. Aditya, Brian, Kevin. Uh, Aditya, do you want to explain what you guys did in your team and what's your answer if you have come up with? Aditya?
Sorry, my mic wasn't working. I think another person might be better off answering the question. I'm not too sure about this one.
Okay, all right. How about
Professor, can I try?
let me go to Brian.
Hi,
Brian,
hi again.
Brian, did you guys come up with some conclusion on this problem?
No, but I tried. I started it, but looking at the I'm looking at the label fact.
Mhm.
We're setting this. We're storing all the registers and words
Mm-hmm, mm-hmm.
into the.
Okay, okay, that's okay. Kevin, you have anything to share? Kevin Trin?
I didn't really understand the problem.
Okay, all right. How about SG5? Ekta Halani, Patricia Saito. Patricia, do you have anything to share with class on this problem?
I also didn't know how to solve it.
You haven't? Okay. How about Ekta?
I'm not really sure either on how to do.
Okay. I think Rahul, you were trying to volunteer, right?
Yeah, I had an approach. I don't know if it's right, but it was just a gambling gamble I tried. But I want to check whether or not my gamble worked. So I tried to look at the whole thing, and now there were a bunch of things that I did not understand. But here's what I did understand: the first section, where all the stuff or where data is being put in the memory,
Mm-hmm.
that part is important. So in the first section, 20 bytes of memory gets used up.
Mm-hmm.
Now that's the only place where memory is getting used up. That much I understand. But then here's the thing: because there's a fact, um, there's the recursive element. Uh, I tried to find out how many times the same function was being called,
Mm-hmm.
and from the BLT, which I do not understand the comment, but thank you for that comment. I don't understand the instruction, but from the comment, I'm guessing it's going to be n times. So since the input value is 10, like a naught starts with 10, this thing, I mean, it's sorry, the recursive, it will recurse 10 times, and that means 10 times it will store 20 bytes in the stack memory. So 10,
Okay.
20, 200. So I'm
Mm-hmm.
guessing 200 bytes at max, at peak, 200 bytes will be used up in the stack.
Okay. You have right approach, but I think you haven't come to an conclusive answer there. It's not 200 byte. It's a little bit more than that.
Then 210, I'm assuming I'm making off by one arrow in the number of recursiveness.
Um, it's let's see. Yeah, why don't I explain? If anyone wants to volunteer, jump in. You can. Otherwise, I will try to explain it to you guys.
I do have a quick question.
Yes, Andrew.
At inside or the opening or the statement at the beginning is you add add IU A0 register 0 10. So you're setting the initial value of A0 to 10.
Right.
And that's the value that we save.
That's the argument we are passing into that factorial.
Okay. And then once we begin fact, and then we run through add I, s stack pointer, save word, and all that, the value of A0 that we save inside the memory, is it 10?
What do you mean by inside the memory? Like register is not a part of memory. It is a register.
I think I'm just confused.
Okay, why don't I just explain? Okay.
Okay. Well, in that case, let's see. The A0 and the one we call branch less than BLT. Is that 10? Because we're comparing it with T0.
Yes. Yes.
Okay. Okay. I see.
A0 is 10 in the sense like it depends on the call, right? If you see that it is a recursive call, JL fact, and each step we are reducing the A0 by 1.
Okay, I think I get it. Thank you.
Okay. All right. Okay.
Professor?
Yes, Rahul.
One more. I think I realized my error.
Okay. What was
Correct.
your...
Okay, so the BLT thing, it has 10 checks for 1098 all the way to 1, but then it will also have one check with 0 where it's going to fail. And that's, yeah. So I assigned 20 bytes in the stack memory for the 1098 all the way to 1, but I forgot to assign for 0, and the 0 will also assign, so 220 bytes.
Okay, okay. The answer is less than that.
Okay. Okay. Yeah. All right. I give up for now.
There is a little bit trick there. Okay, in this question, like it is a matter of like what is being called as a consumed memory. Okay, let me explain it. So in this problem, you need to understand one point, right? It is talking about how much stack memory usage in this procedure. And mostly for a given function, unless it is a very specific special function, any procedure or implementation has the stack memory consumed by the frame creation. Okay, so in this case, your frame creation is coming from this part, right? Your RT storage code. And clearly, like in any function, not only for this function, any function on the stack memory side, let's say this is the memory, okay, and you are storing storing the frame inside the stack memory, maybe about this, right? This is where the stack pointer was, and now you move the stack pointer to here, right? So this part you are storing, you are consuming the memory, all the store word. But you see, you are actually storing 4 byte less, right? You are storing here, how many variable you are storing? 1, 2, 3, 4. So 4 multiplied by 4, 16 byte you are storing. So this part is practically a 16 byte. But your stack pointer is moved to one space below. Now this is at this point, this is a free space. Why? Because someone can push a variable into this point, like it can be used. It is not consumed at this point. Now let's say this function, whether it is recursive or not, that's a different story. Let's say this function is calling another function. And at that point, your frame will be stored here, and your stack pointer will be moved into this point. Now, at this point, we cannot say this part is a free space. This is consumed because you cannot access it. A program cannot access it through the stack pointer. And that's why you see there is an extra space consumed if this function is calling another function from within inside it. So it becomes really a 20 byte consumption at that point. But at this point, it is 16 byte. So total memory consumption is, till this point, is 36 bytes. So with the same notion, now let's see what this function is doing. So your function is called with A0 10. So that is one frame creation. One time it is iterated. And then you see there is it calls itself by decreasing the A0 value. So A0 become 9, 8, 7, etc. till it hits this condition. If A0 is less than 1, like T0 is loaded with 1, so if A0 is less than 1, means A0 is 0, then we basically terminate this one, like this one become a terminal condition and recursive. And since this is a recursive call, the function itself calling itself, so it will start rewinding on the stack at that point. So that means how many times this frame will be created. So it's basically 11 times, right? It is not, it is passed as 10, but it is the first main function call already called it. So it will be something like, let's just do the handle motion. Next iteration is a 9, then 8, then 7, another 6, another 5, another frame, 4, another frame, 3, another frame, 2, another frame, 1, another frame, not yet done, one more, call, 0, another frame. So how many frames are actually created throughout this call for this example is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, straightforward way, what you can think that, as Rahul was mentioning, is that you see the stack pointer is moving 20 bytes on each recursive call into it. So straightforward calculation would be total it's not total, it's a peak stack would be peak stack memory will be 11. We are creating 11 frame multiplied by 20 each time 20 is moved forward minus 4. The last frame, that extra 4 byte is not consumed. So it is 220 minus 4, 216 bytes. Rahul, do you agree?
This makes sense considering that 4 byte was left out, but I have a question. I'll ask after the explanation.
Sorry, I couldn't hear you properly, Rahul. Can you repeat your comment?
Yeah, so far I agree. This makes sense considering that 4 byte which was left out. But then I have a question regarding that, and I'd like to ask that after the explanation, if there's more explanation.
No, I think I'm done with this explanation. Tell me.
Neat. All right. So that 4 byte, that extra 4 byte being left out, is that an artifact of only this particular function, or is it some form of convention?
As a free space or like
As the free space, the extra 4 bytes which was left out unused in each
yeah,
block.
it's by the convention. Like it's we are pointing to a space. We are setting up the stack pointer in such a way that someone can push a double word onto the stack safely without like knocking through the frame, overriding the frame content. So
Okay.
it is by convention. You're leaving out that free space out there after the frames.
So again, also by convention, when we are doing a push operation to a stack, we first move down the size we want to push and then we push, correct?
Right.
Yeah. If that is already a convention, then isn't this kind of redundant? Because
No,
suppose no space was left out, then someone wants to push a double word, they would first move down a double word amount and then push a double word.
no, but push is a byte. Sorry, push is a word, right? It's a if you are pushing, it's kind of saying that you the convention wise, like if the stack pointer is pointing to a space where if you move 1 point down, you are kind of safe to put the data into the memory altogether, right? Now, what you have said is also valid. It's not incorrect. Okay, it's depending on who are using that push, right? It's basically whether you want to put this on the client side or user side, where who is trying to put a double word push into that memory, or you are basically doing the job for them. Depending on that, you can stick to a convention. Okay, there is nothing, I would say, strict rules about this. Okay, even with that convention, you could not even just have that free space at the end at all, right?
Yeah, and that's what I was saying. Because
Yeah,
why leave empty free space which is not going to be used?
exactly. So this is again that for the convention of the double word push, which basically using the similar code, you just move the pointer one down and push it into the stack. That will also suffice for the double word size to follow to kind of fulfill that destination, basically. Okay, so what I want to say here, it is there is nothing right or wrong about this convention. It is more like that, like those kind of situation where either party is right, nothing wrong. Okay,
I
so
see.
we are just following one convention in this class.
Okay. And so when we write our functions for assignments and stuff, should we leave that extra 4 bytes?
Yes, please, because remember, like you may not write code from the scratch. Like I may give you some code, other people may give you some code, and we need to be on the same page about the convention. We need to follow the same convention, and that's the importance of it.
I see. Okay. So for this class, the convention is to leave the 4 bytes of space.
Exactly. You got the point correct this time. Yeah. So for this class, like why I have this convention, just to make sure that you get this point that when you are in a world of software writing, you are not the only one person who writes the entire software. Like it's the like multiple people contributes to the software code. That's why it is very important to stick to the convention. Whether that convention makes sense or not, that's a different story. And at some situation, it may be neither party is right or neither party is wrong. Like it's that kind of situation, and that in practical life you will also face this kind of situation. So take out from this whole discussion is that it is important to follow the convention that is being laid out.
I see. And Professor, again,
Yes.
I just realized, considering considering this code will be executing as part of a system where the convention is already being followed,
Mhm.
when the function is called, it will already start with 4 bytes above it. So considering that when we place the 16 bytes, we should already start with 4 bytes on top. But over here, we're starting as if we're not starting with any extra space on top.
Yeah, that's why like we are leaving the 4 byte space, free space through that convention. Otherwise, we need to leave the 8 byte free space. Remember, our target in this convention is that to set a pointer in such a way that we should be able to push uh, like double word at that position without stepping over the frame. So with that convention, right, it would become like a +8, like frame size +8. But since we already start with one 4 byte free at the very beginning with our convention, that's why it become frame size +8 -4. So that is why it is frame size +4.
Okay, so between the data of each recursive element, there is technically going to be 8 bytes of free space.
Between, yeah, but
Of two different programs, of two different functions. Over here, the same function is
right.
recursing, so 4 bytes.
Right.
But if you have, I see. Okay. All right. Thank you.
Okay. All right. Then what else? What else we want to do here? Any other questions from any of you? No. Okay, then we can actually stop tonight a little early if we don't have any other question. And then we'll all see you on next week. But remember, tonight there is a programming assignment due, and I believe there is a quiz, right? Quiz 3. Is it? Let me check.
I think quiz 3 is due tomorrow.
Well, it's due on Saturday.
Yeah, this Saturday, right? This Saturday, like it will open up on tomorrow. Yeah, tomorrow morning, and your due date is Saturday night. So make sure you don't miss them. All right. Okay, then good night, everybody. And